This is our 6.6 part 2 video. This section is talking about de Moivre's theorem and complex numbers. We just at the end of the last video did this problem where we used de Moivre's theorem, and from de Moivre's theorem you can basically get to the idea of nth roots of a complex number. And we're really going to use this bottom box here that says if I have this complex number, basically I can create this pattern that will let me find the, however many roots I want to of that number. And so we're just going to dive right into one of these problems right here up at the top. Now, so I moved the second example down a little bit because I didn't quite have enough room when I tried to write it out. So you might have enough room, you might not if you printed out the notes, but just kind of be aware that's the case. Also, I copied this right here from the previous slide so that I could see it to use it. And so that's why it's not there on yours, but it is on mine. So we are finding the cube roots of the complex number. So cube roots, that's the third root. That tells me that my n is going to be 3. Okay, so the square root, I would have n equals 2, the cube root 3, the fourth root 4, and so on and so forth. That's this n that's in our formula over here, basically. Then if I think about a normal complex number in trig form, my 3 is my r, 4 pi over 3 is my theta. And now what I'm going to do is plug in r, theta, and n into this formula I have. So I have the nth root of r, so that's the third root of 3. And then I have cosine of my angle, which is 4 pi over 3 plus 2 pi k. And we leave the k as k. We're going to deal with that a little later. Okay. And then the n on bottom is this n right here. Then I sine 4 pi over 3 plus 2 pi k over 3. Okay, and then what we're trying to do is we're trying to plug in values of k from 0 until 1 less than n. So 0, 1, and 2 is what we're going to plug in, and that's going to give us 3 answers, because if I'm doing cube roots, I should get 3 different cube roots. Okay, so if by plugging in 0, 1, and 2 to this formula right here, I can get 3 answers. But it would actually be easier for me to do if I would simplify this massive thing right here before I do that. Because that will save me time. Basically, I won't have to simplify 3 different times. If I simplify once right now, then I won't have to simplify as much later on. So remember that if I have 4 pi over 3 and I'm trying to add 2 pi k, I would make this into a fraction, put it over 1, and then we want to get common denominators. So I want a 3 on the bottom of my second fraction. That gives me 4 pi over 3 plus 6 pi k over 3, still over 3. And then I would just combine the two things on top here, 4 pi plus 6 pi k. I can't actually put those together because of that k, but I can set them next to each other on top of a fraction. This is over 3, which is really 3 over 1. I can flip that and make that a 1/3. So that on top here, I have 4 pi plus 6 pi k times 1. Okay, so that's just 4 pi plus 6 pi k. On the bottom, though, I have 3 times 3, which gives me 9. So this is what I'm going to put in for my angle now. So I have the cube root of 3, and then I have cosine of 4 pi plus 6 pi k. Yeah, that's totally a k. Over 9. Plus I sine 4 pi plus 6 pi k over 9. Okay, and now I'm ready to plug in 3 things. I want to plug in k equals 0, I want to plug in k equals 1, and I want to plug in k equals 2. And so when I plug in k equals 0 in the book, the way it labels it is it labels this first answer as z1 because it's a complex number z, And it's our first answer we're getting, basically, is why we're calling it Z1. We're going to plug in that k is 0. So the cubed root of 3 is not going to change at all. That's going to stay the same. You have cosine. Now if I plug in 0 where k is, then I get 0 times 6 pi, which is 0. 0 plus 4 pi is 4 pi. 4 pi over 9 stays 4 pi over 9. So for my first one, the angle is 4 pi over 9. And on these, that's a 9. The only thing that's going to change between my three answers here is going to be this angle. Okay, so now let's put Z2. For Z2, I'm going to plug in a value of 1 where k is. So I still have the cube root of 3. And then I have 2 pi times 1, sorry, down here. 6 pi times 1 gives me 6 pi. 6 pi plus 4 pi is 10 pi on top, so that's 10 pi over 9. Okay, so that's Z2. And then I would plug in k equals 2 and get Z3. So that's the cubed root of 3. And then cosine. And so when I plug in k is 2, I get 6 pi times 2, that's 12 pi. 12 pi plus 4 pi is 16 pi on top. So that's 16 pi over 9. Okay, and so these are my three answers. Z1, Z2, and Z3. Those are the three cube roots of the complex number that they gave us. So now let's, that was that first example. Let's do this bottom example now. So find the fifth roots of the complex number. So Rn is 5. Okay, the next thing we did in the last problem is we looked at the r and the theta, and oh, 2i, that doesn't have an r or a theta. So the first thing you're going to have to do actually is turn this into trig form. So 2i does not go left or right, it's a point up here. Okay, that's 2 up. So that would have a magnitude of, if we think of it like 0, 2, then it'd be 0 plus 2 squared, taking the square root. That ends up being 2 for r. And then this angle here in radians is pi over 2. So our theta is pi over 2. So we're actually doing the fifth root of 2 cosine pi over 2 plus I sine pi over 2. If you don't understand how to get the trig form, that was in the first video of 6.6. So go back and look at that again. Now we're trying to use this formula that was up at the top. This one right here. Oh look, here it is again. Okay, we're trying to use this formula to figure out the 5 fifth roots of this complex number. So we know n, we know r, and we know theta now. So let's do this. This is going to be the fifth root of r, which is 2, times cosine of our angle, which is pi over 2, plus 2 pi k over our n, which is 5, plus I sine pi over 2 plus 2 pi k over 5. So again, our first thing we want to do is simplify pi over 2 plus 2 pi k over 5. Because if we simplify it once, then we don't have to keep doing it this time for our 5 answers. Okay, so I want common denominators, so I need to multiply the top and the bottom on this one by 2. So that's pi over 2 plus 4 pi k over 2. It's all over 5. And so that makes it pi plus 4 pi k over 2 over 2 over 1. We can flip this up and do times 1/2. So this is really pi plus 4 pi k over 4. So let's put that back in. 5 roots of 2 cosine pi plus 4 pi k over 4 plus I sine pi plus 4 pi k over 4. Now, what k's are we trying to get? We're trying to go k equals from 0 until 1 less than n. So that's 0 to 4. So for k equals 0, we have our first complex number, which is going to be the 5th root of 2 times cosine of, if I'm plugging in 0, then 4 pi times 0 is 0, which gives me just pi over 4. And I actually can figure out what those values for cosine and sine are using the unit circle, but let's just leave them for now alone. So then k equals 1. So my second complex root is the 5th root of 2 cosine. Now I need to plug 1 in where k is up here. So 4 pi times 1 is 4 pi. 4 pi plus pi is 5 pi on top, so that's 5 pi over 4 for my angle. And again, this one's on the unit circle, so we could look that up on the unit circle and figure out what that is. Now I want to do k equals 2. So this is our third answer. So this is 5 on the 5th root of 2 cosine. We're plugging in k is 2. So up here, 4 pi times 2 is 8 pi. 8 pi plus pi is 9 pi on top. So this is 9 pi over 4. And let's just keep going. Now we have k equals 3. We're on the second to last one, so z4. So that's the 5th root of 2 cosine. I'm plugging in a 3, so 4 pi times 3 is 12 pi, plus another pi is 13 pi. So that's 13 pi over 4, plus I sine 13 pi over 4. And last, k equals 4. It's going to give us our 5th root. Our fifth root. Anyway, so 5 root 2 cosine. We're plugging in 4. 4 pi times 4 is 16 pi, plus another pi is 17 pi over 4, plus I sine 17 pi over 4. So there are the 5 roots, the 5 fifth roots of the complex number we started off with, which was 2i. And on each of these, we could go a little bit farther. We could look up the values on the unit circle and kind of get even a more simplified answer, but that's the basic gist in trigonometric form of what we would get. And really, we would only do that if they ask us for the standard form. If they ask us for the trig form, this is the trig form, even though we can find those values on the unit circle. So the last thing that we are going to talk about is expressing roots of unity. And so that sounds like it's kind of crazy, but if it wants roots of unity, it's asking for like unit roots. And so anytime you hear the word unit, you should think 1. So basically what we're doing is we're going to find all of the, in this case, 4th roots of the complex number 1. Okay, and you might say, well, that's not a complex number, but it is, because we can add a 0i, and now 1 plus 0i, that's a complex number. After we're done, it wants us to graph each root in the complex plane. What's cool about this is when we graph these, they're going to end up being in a circle. since it's the fourth roots of unity, they should end up in a circle like where they're an equal distance apart. Well, all of them will end up an equal distance apart, but like fourth roots of unity, it should divide our graph into like 4 equal parts. So we have our goal here. When you see of unity, this is what you need to start off with, is z equals 1 plus 0i. We actually, though, we need the trig form of that, right? So 1 plus 0i means we went right 1 here, and so that means our r is 1 and our theta is 0. Well, that sounds simple enough. So in trig form, that would be 1 cosine 0 plus I sine 0. Now, we're finding fourth roots, so our n is 4, and we're using that formula that we've been using. Ta-da! Copy and paste is a wonderful thing. This formula right here. Since it's fourth roots, then we should be plugging in k equals 0, 1, 2, and 3. Because we're trying to get 4 answers, so that's the 4 numbers we're going to plug in. So the fourth root of 1 times cosine of 0 plus 2 pi k over n is 4. The same thing for sine. So if we simplify our angle on this, 0 plus 2 pi k is just 2 pi k. 2 pi k over 4 is 2 pi k over 4 is pi k over 2. Because basically I said ignore the 0 because 0 plus doesn't matter. 2 over 4 I can simplify into 1/2. So I got pi k over 2. Now the fourth root of 1, you may or may not realize, is 1. Okay, and so now we're just plugging in our values for k. We have k equals 0, which is going to give us our first answer. We have k equals 1, which will give us our second answer. We have k equals 2, which will give us our third answer. And we have k equals 3, which will give us our final answer. So when I plug in 0 here, right here, basically we can ignore this 1 on the outside and just write the inside, I guess. Or we could write the 1 on the outside. I mean, that makes it a little bit more true to the trig form. Kind of depends. I think, though, we'll end up with standard form. So maybe it would be best not to write 1. We want standard form so that we can graph these. So ignoring the 1, because it doesn't matter, cosine of, if I plug in 0, that gives me 0 over 2, which is 0. So this is my first one. We'll simplify using the unit circle here in a second. If I plug in 1 for k, that'll be pi times 1, which is pi, so pi over 2, so cosine of pi over 2. If I didn't mean to put that blue dot there, ignore that. If I plug in 2, that gives me 2 pi over 2, which is just pi. Okay, if I plug in 3, that's 3 pi over 2. Now let's simplify these using our unit circle. So cosine of 0 is 1, and the sine of 0 is 0. So we end up with 1 plus 0i, which is what we started with, right? So that's actually just 1, if you want to think about it like that. On the next one, the cosine of pi over 2 is 0, and the sine is 1. And so that's really just I. And then for pi, it's -1 and 0. So that's really -1. And then for 3 pi over 2, it's 0 and -i. So that's -i. So these right here are our 4 roots of unity. Our 4th roots of unity, I mean. These are our answers. Now it wants us to graph these. Well, this one's really easy. The other roots that we have weirder numbers, so it's kind of harder to graph. But like, if I make a tick mark where 1 is all the way around, okay, then I actually have a point at 1 plus 0i, which is right here, at 0 plus I, which is here, at -1 plus 0i, which is here, and at 0 minus I, which is here. And so we actually do end up like all of these are on this like unit circle, basically. A unit circle meaning a circle with a radius of 1. And so that's all that she wrote on this one. Finding roots of unity, finding whatever roots, complex numbers. Awesome. Yeah.